Okay, lesson 9 is on the initial rates method. We'll get into that in a little bit, but before we do, a reminder that on April 27th, if you're watching this after that or before that, that's when our test is on Sapling. Video directions on the test procedure is posted, so make sure you know how to do that. The homework for this lesson isn't due until May 1st, and it will be via Blackboard, the same manner that the previous homework was done. Okay, let's see. Next week, in addition, Zoom on Wednesday and Friday is office hours. Okay, so last time we went over differential rate laws. Differential rate laws link the rate of a reaction, okay, to the reactants. And remember, it's called differential because in it we use difference, right? Negative delta A delta T, or dA dt once we talk about differentials, right? We make sure that time is so small that we can talk about differentials, okay? We have these variables K, M, and N, okay? Where K is our rate constant. We find this experimentally. M and N are what we call rate orders. These can be 0, 1, 2. They can be more complex, but those are usually the ones. The overall rate order is found by summing up all these other rate orders, okay? And so we take the concentration to these rate orders. For instance, concentration A and B. These are only for the reactants, not the products. And the last thing is M and N, these are found experimentally. We don't know these based solely on that reaction. Okay, so the review that we had on this kind of talks about which of these are second order. So we have some variables down here. If I have rate equals Ka2, this is a second order reaction. Why? Because it's something to the second power. In addition, number C is second order because I have the first order for this one and first order for that one. So the sum of these is going to give me 2. The others on that list are not second order. This one, rate equals KOH, that's first order because that OH is to the first power. If I don't have anything listed, that's the first power. Okay? Why? Because 4 to the first power is equal to 4. So we don't even include that. All right, this one, rate equals K, that's actually 0 order. And this one here, rate equals K times A times B times C squared times D to the cube, that's actually 7th order because it'd be 1 plus 1 plus 2 plus 3, right? This would be a very complex reaction that we're not going to deal with here. But we can have things that are really high order. All right, so the second part tells us that we have rate equals Ka squared. This is the differential rate law. And we're asked, what's the value for K under certain circumstances, right? So in A, we're told that rate equals 5 molar per second, and the concentration of A is 1 mole. So if I want to find K, I can rearrange this such that K equals rate over A squared. So now I could plug in 5 molar per second. My concentration of A is 1 molar. I'm going to square that. That's going to get me 5. Notice what happens with the units. Molar over molar squared, that's going to get me molar to the -1 second. Let's look at 2B. In this case, we have a different concentration of A and a different rate. So I can put in 20 molar S-1 and 2 molar here. Now I have 20 divided by 4, so that's going to get me 5 molar to the -1 second. Notice that they're the same. Why is that? Because if I'm talking about the same reaction at the same temperature, the K will be constant. Okay? It does vary with temperature, but in this case, it's constant. right? And notice what happened. My concentration of A, I doubled. So what happened to my rate? It went up by a factor of 4. Why? Because of 2 squared gets me 4. Okay, now let's move on. And now we're going to talk about how we actually find rate orders and how we find rate laws. And we're going to use something called the initial rates method. Okay, the initial rates method looks at a reaction. Let's say we have this reaction. NH4 plus NO2 minus goes to N2 and 2H2O. We're going to do this experiment multiple times, multiple trials of the same experiment. And each time we're going to vary the reactant concentration and we're going to see what happens, right? This is what we do in experiments. We change one thing, see what happens. Change another thing, see what happens. All right, so let's say we have one sets of condition here, different, okay? In each one of these ones, we have different amounts of my reactants, right? And so what I'm going to do is I'm going to look at the change in, let's say, NH4 plus versus time. Because it's a reactant, it will decrease with time. And notice what happens. If I look at the initial rate, right, that's what's happening at the very beginning. And that's what I'm signifying by these curves, right? So at the very beginning, I'm looking and I'm saying, what's the rate here? That's the initial rate. And that initial rate is going to vary based on what my concentrations are. Okay, so we're going to do 2 problems during this video, and then you'll do a problem. And the reason for this is in the initial rates method, it's all about, in order to understand it, you have to do it. Okay, so the first problem we're going to do is we're going to look at that. So we did this experiment 3 times. The first time we had 0.1 molar of my ammonium, and I had 0.005 of my nitrite, NO2 minus. Right? So I put these in my solution, and I looked at what my initial rate is. Right? These are my initial rate. All right, so notice that my concentrations are in molarity. My rate is in molarity per second because rates are always in molarity per second. All right, the second time I changed my concentration, got different rate. Third time I changed this concentration for NH4 plus, got different rate. Okay. By the way, look at these 3 numbers. Which one is the biggest? This one right here. Okay. Remember, this exponent means that this number here is 0.000001, right? So 0.123451112, right? Whereas this one would be 0.0000002, right? Notice this is a bigger number because it's only 10 to the minus 6. Okay, so how are we going to do this? We're going to go through 5 steps to find this out. So I'm going to go do one right now on the screen, then we'll do another on the board, and then you guys can. All right, so the first step is always to write out the generic rate law. Okay? Now, the generic rate law will look like this. The rate equals this value, negative delta NH4 plus over delta T. We don't really need that right now. But the rate equals K, my rate constant, times NH4 plus to some value, times NO2 minus to some order. Okay? I know it's going to look like this. I know it's not going to have N2 in it. I know it's not going to have H2O in it because these are products. It only has reactants. Okay, so now I'm going to take this, and step 2 is I did this 3 trials, so I have 3 different equations. So here, this is my first trial. 1.4 times 10 to the minus 7th, that's my first rate, equals K times 0.1 molar times 0.05 molar. The NH4 plus to M, the NO2 minus to N. I can write this 3 different times, right? Each time my concentrations will change and my rates will change. All right, step 3. Step 3 is the hardest. In step 3, I look at all these now equations I have, and I said, how can I tell something where I kept one thing constant but changed everything else? Okay? So notice between step 1, or trial 1 and trial 2, I kept NH4 plus constant, but I changed NO2 minus. So what that means is this change in rate here is due only to the fact that I'm changing the NO2 minus. All right, so what I'm going to do is I'm going to set up an equation where I take the second trial and I divide by the first trial. And this is going to allow me to find that value for N. All right, so what I do is I take this side, 2.8 times 10 to the minus 7th, over the rate for number 1, 1.4 times 10 to the minus 7th. And then I take the left side of both those right side of both those reactions and put one over the other. K, 0.1 molar to the M times 0.01 molar to the N, and then K, 0.1 molar to the M times 0.05 molar to the N. At this point, I look at this and I say, I see some things that I can simplify. I can see 2.8 times 10 to the minus 7th over 1.4 times 10 to the minus 7th. That's going to give me 2. And I have K over K. So K over K, that's going to cancel out. And notice here I have 0.1 molar to the M, 0.1 molar to the M. These are the same thing. So they're going to cancel out. And so I have now K, this 2 equals this value right here, 0.01 molar to the N over 0.005 molar to the N. Now, when I do this, I will now get this equation. Okay? Now, I need to use some math skills. Okay? If I have this number, 0.01 to the N, and I divide this by 0.005 to the N, that's the same as 0.01 over 0.005 to the N. Okay, that's based on math, right? Okay, so I can do that, and this gives me 2. 2 to the N. Now, once I know that 2 equals 2 to the N, now I can think, what is my value for N? We'll go through how to find this, but I can know that my N is typically going to be one of these values, 0, 1, or 2. Okay? So if 2 equals 2N, it's pretty clear that my N is now 2, right? Because 2 to the 1, or sorry, my N is equal to 1. Why? Because 2 to the 1 gives me 2. 2 to the first power gives me 2. All right, so now I can go ahead and I can plug the fact that I now know that n equals 1, I can plug that in to those 3 equations I had earlier, right? So I have those 3 equations, and now I know that n, which used to be right here, is now 1. Now, I can use this to try to find m. Now, if I want to find m is about NH4+. So I need something where I kept everything else constant, but I varied the NH4+. Notice trials 1 and 2, I kept NH4+, so that's not going to help me. But between 2 and 3, I varied NH4+, but I kept NO2-. So I can use these two to figure out. All right? So now I'm going to take the 1 and I'm going to put it over the other. One trick is I always put the one with the bigger rate on top. Okay, I already did this last time, but the reason being is it gives me a number that's greater than 1. So I'm going to take this value right here and put it over this rate. Okay, that's going to be, so I'm going to take equation number 3 over equation number 2. So the left-hand side, that's 1.12 times 10 to the minus 6, 2.8 over 2.8 times 10 to the minus 7. This equals k times this side right here over this side right here. So I'm using equation number 3 and putting that over equation number 2. Now let's look at this. The k's cancel out. My 0.01 to the first power over 0.01 to the first power, that cancels out. So now I can go, and this right here, if I do that calculation, this gives me 4. And this is going to get me 4 equals 2 to the m. So what value is m? Well, m is now 2. Because 2 to the square, 2 squared gets me 4. All right, so now I have my 3 equations, and I can go ahead and I can simplify these to this. Okay, notice earlier I put a 1 here. Well, that 1 I usually just leave off because it's not even important. Okay? All right, so now I go ahead and I can use these equations to find my k. Here's the trick. Which one am I going to use? I use any of them. So I'm going to use this first one, rearrange it such that k equals the rate over the concentration here squared over this concentration. And that's going to get me 2.8 times 10 to the minus 3. That is the value for my k. That's step 4. All right, step 5 is now to determine the units for k. So now I'm going to use the fact that each one of these has units to do that. So notice this value is in molarity per second. And then on the bottom I have molarity squared from here times molarity. And that's going to go ahead and that's going to get me molarity to the -2 times seconds to the -1. All right, so what does that mean? This is now my rate order, right? So rate equals k times the concentration of NH4+ squared times the concentration of NO2-. And now we could even use this if, and we did this last time, if let's say I wanted to go ahead and I wanted to do a 4th trial where I knew the concentrations of NH4+ and NO2-, I could go ahead and plug those in. This would be 1 squared times the concentration of NO2 minus, and my K would be the same. So I could take this K value times 1 times 2, and I would get the rate for my trial number. Okay, so this is the initial rates method. I go ahead and I write out the generic rate law. Then I write out the rate laws for each one of those trials. I solve for each of the orders. Then I finally get K and the units for K. All right, here are those steps right over here. Okay, so let's do the problem number 2. If there was a cut, it's because I had to restart this problem. So we're looking at I minus plus OCl minus going to form IO minus plus Cl minus. Now, in reality, I don't care about the products, right? In the initial rates method, we only care about the reactants because the reactants are the only ones that are in that rate law, okay? But I have them up there. So step 1 is a generic rate law. So I have rate equals K, step 1, rate equals K times I minus to some power M times OCl minus to some power N. Okay? Now, if this had another reactant, I would have another concentration, right? And, you know, H2O to the power of P, and I need to find that. But this only has 2, so I only have 2, right? So I put in the concentration for all of them raised to some power. Now, in some things, they use X and Y. Some they use A and B. Here, we just use M and N. It doesn't really matter. Okay, so we have that. So now let's move on to step 2. Step 2 is to go ahead and plug in for each one of those trials. Okay, now be a little bit careful because notice how when I look at that page, right, the initial rates is in the table at the very end, right? Whereas when I have it on here, it's the first thing. So be very careful about that. So that's 1.4 times 10 to the minus 2. I'm not going to include the units now. I know I've harped on that a lot, but it's easier just to do without units and then use the units later. Okay? So this equals K times 0.12 to the M times 0.18 the N. Second, I have 7.1 times 10 to the negative 3 equals K times 0.06. I'm going to leave off that extra 0 because I don't need that right now. Third, I have 8.9 times 10 to the minus 4 equals K 0.03 and then 0.09 to the N. Okay. And then finally 7.0 times 10 to the minus 3 K 0.24 to the M times 0.09. Okay, so I have these 4. Now what I'm looking for in step 3, what I want to do is I want to look and I want to go ahead and I want to see, hey, what can I use to figure out M and N? All right, so let's go ahead and look at this equation, these equations here. Notice in the first 2, I have the same OCl minus, right? But I'm changing my I minus. So what that means is any change in the rate is due solely to changing the I minus. Okay? In 3 and 4, I kept the OCl minus constant again, changed I minus, so any change in the rate is due solely to the I minus. but no point did I actually keep I minus constant. So that's going to be a little bit difficulty later on. But for now, I can use the fact that in 1 and 2, I kept OCL minus constant to figure out how this rate law behind me is affected by I minus. That's M. Okay, I could use 3 and 4, but I'm going to use 1 and 2. All right, so what I want to do is I want to use 1 and 2, and I'm going to use these two. And so what I'm going to do in step 3, I'll call this 3A, I'm going to put number 1 over number 2. The reason why I do 1 over 2 is I want the faster rate to be on top. The reason being is when I do this, I want to get a number that's greater than 1. I'll explain later on why this is the case. It works either way, but it's just a little bit easier. Okay, 0.12 to them. I know it's fun to watch someone just write on a board, but you'd be doing that in class if we weren't going through all this. So it's kind of like what you would have, what you're missing with all of this. All right, so I have this, and now I go ahead and I look at what's constant. So my k is constant, so k over k gets me 1. 0.18 to the n over 0.18 to the n, that cancels. All right, so now I have this over this and this over this. So I can go ahead and I can use 1.4 times 10 to the minus 2 over 7.1 times 10 to the minus 3. This gets me 1.97. This is 0.12 the m over 0.06 the m. Now we're going to use some math. And notice that these are to the same power. So what I can do is I can just do 0.12 over 0.06. So this will give me 1.97 equals 2 to the n. Okay, so now I need to figure out what the value for m is. So I'm going to erase this real quick and do this. What happens when you get a nicer pen that's a little darker, it's harder to erase. All right, 1.97 equals 2 to the n. So now I'm going to go through a little bit later a more complicated way to figure out m, but the easiest way is just to use what I said earlier. M is usually 0, 1, or 2, right? In this class, in the lecture, you're going to see it as 0, 1, or 2. So let's use that. So if m is 0, that would mean that 2 to the 0 equals what? Any number to 0 equals 1. Right? 532 to the 0 equals 1. 283.460 to the 0 equals 1. Elephant to the 0 gives you 1. Okay? So 2 to the 0 equals 1. So does that mean m is equal to 0? No. Because I say it should be equal to 1.97. Okay? All right. How about m equals 1? 2 to the 1 is going to give me 2. Well, that's pretty close to 1.97. Any number to 1 gives you that number. All right, that's pretty close. So maybe that's right, but we'll go in and we'll look at that later. How about m equals 2? Right? These are the three possibilities. 2 to the second power is going to give me 4. So I know it's not 2. So it's not 0, it's not 2, so that means it's 1. Okay? Now be careful. This is why I had to do another cut. This doesn't mean m is equal to 2. What it means is m is equal to 1. Right? So the fact that m is equal to 1, I can now plug that in there. Right? What I did last time, we all have our moments, right? I said, hey, m is equal to 2, so I started doing stuff, and it took me another 10 minutes to figure out I was wrong. And then I got depressed, so I had to stop tape. I had to drink a little. No, wait. All right. So now that we know that m is equal to 1, I can put in a 1 here. Okay? But now, in reality, I'm not even going to include that because for the same reason I don't include a 1 here, right? It's assumed, right? Or it's just there. So I minus to the 1 is just the same as I minus. Okay, so now I'm going to go ahead and I'm going to write down those other 3 equations. These are the other 2 equations. These are the ones I had earlier. 0.03, 0.09. Okay, so now, actually, I'm going to only write down this. Remember what we said. We said there's no time when we have I minus constant, right? So what that's going to mean is I can't just say, hey, like I did earlier, hey, these 2 are constants, so only effect of this, right? But if I look at 2 equations, such as these 2, where I change OCL minus, I now know what the effect of changing I minus will have on this, right? So I can figure this out, right? So I just need something where the OCL minus changes. So I could do 2 and 3. I could use 2 and 4. I could use 1 and 3 or 1 and 4. I'm going to use 2 and 3. Okay. All right. So I'm going to call this 3b. Right. 3a. We found out that n is equal to 1. All right. So now we're going to try to find n. And so I'm going to use 3 and 2. Which one am I going to put on top? I'm going to put the one on top that has the faster rate. That's number 2. Be careful, by the way, because sometimes I haven't had to stop the video because of it, but sometimes I'll use these numbers. These are just identifiers, right? I don't include these in my actual calculation. All right. So I put my rates, k, 0.06 times 0.18 the n, k, 0.03, 0.09. Okay, so now I do the math. 7.1 times 10 to the minus 3 over 8.9 to the negative 4. It's going to get me 7.97. Or 7.98, sorry. Notice the k's cancel out, right? These don't cancel out. Last time, when I looked at these 2, they cancel out. Here they don't. And that's why, if this were m and m, I didn't know what these were, I'd be in trouble. But seeing that I already know what m is, I don't have to worry about that. All right, so that means that I have 0.06 times 0.18 to the n over 0.03, 0.09. All right, now what you're going to be tempted to do, because I'm always tempted to do it, is take this 0.06 and multiply it by the 0.18. But you can't do that. That's not allowed. So what I need to do is I need to go ahead and just say, okay, I can't do that, so let's go ahead and get rid of these. Right? So this will be 7.98. I can go 0.06 over 0.03, that's 2. All right? And now I have 0.18 over 0.09. I can group these 2, but only because they're the same power. I can't group this with this because they're not to the same power. Okay. All right, so now I have this right here. From here, I can divide by 2. That's going to get me 3.99 equals 2 to to the n. All right, and now I go ahead and I figure out what my value for n is. So if it's 2 to the 0, that would be 1. 2 to the 1 would be 2. 2 to the 2 would be 4. All right, so that means that n is equal to 2. All right, so I just found out that n is equal to 2. Okay, so we found out what m is. We found out what n is. Now we can finally find out what k is. That is step 4. All right, so I have these values. I have these equations. Now I can use them to try to figure out what my value for k is, right? Because my k is going to be equal to the rate over, this is step 4, the rate over I minus times OCL minus squared. Okay? All right, now I can now go ahead and I can plug them all in. Which one am I going to use? The truth is I can use any of them, and they should give me the same value. I'll actually show you this afterwards. They'll give you some slightly different values, but they'll all give you almost the exact same value for k. Why? Because k is a rate constant, so it should be constant. All right, so I'm going to use number 1. That's 1.4 times 10 to the minus 2 over I minus, for this equation is 0.12. This one's 0.18 squared. That's going to get me 1.4 times 10 to the minus 2 over. Be very careful. Don't just plug all this into the calculator in one go. Make sure you take each step and you're not messing it up as you go. So I'm going to take that, divide by 0.003888, and I get 3.6 for my value. Okay. All right, now, I was just making sure I did it right. Okay, so that's 3.6. That is my value for k. But step 5 is I need to find the units. Okay, so I'd say this is 3.6. In the same way, remember at the very beginning I said I'm not going to use units. Now I go back and I say, oh, these do have units. So now my k is equal to this is molarity, second minus 1, this is molarity, molarity. So my k is going to have units of molarity, seconds minus 1, over molarity times molarity squared. This is going to get me molarity, seconds minus 1, over molarity cubed. Okay, so I have 1 over 3. So that will be 1 minus 3. So that's going to get me molarity, the minus 2 seconds to the minus 1. Right? So that's my units. All right. So what's my final answer? My final answer is that for this reaction, here's my rate. Right? My rate is equal to k times I minus times OCL minus.
Word.
And I know my value for k. My value for k is now 3.6 molarity to the minus 2 seconds to the minus 1. Right? That's my answer. Right? Let's go ahead and look at this on the screen just to make sure we understand it. And then, yeah. Okay, so first thing we do is we write out a generic one where we put m and n. Notice the generic doesn't include anything to do with the products. I never talked about IO minus. Now, I go ahead and I use all this data to come up with 4 equations, each one for each different trial. Now I go ahead and I use some of these equations to try to figure out m and n. So I first use number 1 and 2 to find m, because my OCL minus was constant, so those cancel out. My k's cancel out, and I can find the value for m. Once I know the value for m, in this case it's m equals 1, now I can go ahead and I can put a 1 in place of all those. And so now I can go ahead and use I use number 2 and 3 to figure out the effects of n, right? Because the k's cancel out, and I can go ahead and find n. In this case, n is equal to 2. So my final, so this is my rate right here, number 3. Step 4 is I solve for k. And so on the board I use this, trial 1. Okay. Trial 2, if I plug in that, I get something that's slightly different, but it's close enough. Remember at what we said. We said there's going to be some slight error, but these are very close. If I got 3.6 for this and I got 3.2 for this one, that's too far off. If they're within a rounding error, that last digit, it's usually fine. Okay? All right. So if they are wrong, if I got 3.6 and 3.2, then I'd go back and I made sure I didn't mess something up, right? Because if that happens, that's how I can tell that I messed something up. And then finally, I get the units. Okay? And I get the units by plugging in the units for all those things that went into the value for k. Okay. Now that we've done 2 problems, let's go ahead and look a little bit more at finding orders. Okay? So we've gone through this a few times, but I just want to make sure we get it, right? So let's look at a simpler equation. Let's say we just have something where we're told that rate equals k times a to the m. So this is an equation or a reaction with only one reactant. Okay? That reactant is compound A. All right, so we do 2 trials. The first, we have a concentration of A of 1.8, the second 4.2, and we get 2 different rates, 2.3 and 12.4. So if I do trial 2 over trial 1, what I'm going to get is 12.4 over 2.3, that's going to get me 5.39, equals K times 4.2 to the M over K 1.8 to the M. The k's cancel out, so this gives me 2.33 to the n. Okay? Like I said, typically this is either 0, 1, or 2. So I can go ahead and I can plug in, right? Here, if m equals 0, this 2.33 to 0 will give me 1, right? What this means is that the rate doesn't change with a change in concentration, right? This would be only if a case where we changed the concentration of A, but my rate remained at 2.3. Okay? Changing that concentration had no effect. But that's not the case here. All right, so it's not 0 order. Let's try first order. If m is equal to 1, that'd be 2.33, right? So it's not this. Okay, so it's not first order. But if it's second order, if m equals 2, that'd be 2.33 squared would be 5.42. Okay? These are close enough that I'm going to say m is equal to 2. Remember what I said. In lecture, I'm either going to say it's 0, 1, or 2. Right? In lab, it could be a little more difficult. Okay. Now, there is one life hack we should think about. Remember what I said. Always put the faster of the 2 on top. The reason this is the case is because it just makes the math easier to visualize. Let's say instead I put trial 1 over trial 2. Right? If I had this, it'd be 2.3 over 12.4, and that would get me 0.18. Okay? And then when I do that, it'd be 0.18 equals 0.43 to the m. Okay? This will work the way we just did it, but it'll be a little more complicated because what it's going to be is notice how 0.43 to the m equals 0.18. It's not very easy to figure that out. Whereas here, when I see 2.33 to the m equals 5.39, I can tell right away that it's probably 2, right? But 0.43 squared equals 0.1849. So it does work, it's just a little more difficult. So usually put the faster rate on top. Okay, now there is one other way to figure out m, and this is something that can be helpful in lab. Okay. So let's say, again, we come up with this, where we have 4.96 equals 2.33 to the m. Another way to find m is to use a trick that we learned in math class. And that's that if I take the log of a value, right? So if I have log of x squared, that's going to be equal to 2 times the log of x. So if I take 4.96 equals 4.96 equals 2.33. If I take the log of both of these, I can go ahead and rearrange this, right? Such that log of 4.96, which I can do in my calculator, and that's 0.6955. This equals m times the log of 2.33. Okay? I can move this m out to the front. Okay? Now, when I do that, what that does is I can now say 0.6955 equals m times 0.3674, right? I took 2.33, I found the log of that. We will be using logs more in the upcoming weeks, so make sure if this is like new to you or you haven't used it in a while, figure that out. And that means that m is equal to 0.6955 over 0.3674. Plug those in. Okay. And this would give me m is equal to 1.9. Okay. Now, remember what we said, m is equal either 0, 1, or 2. So I can then say, okay, my m is equal to 2. All right, this is helpful in lab because a lot of times in the lab, seeing that you're looking at data, it's not going to be really close to it, so it'll be a little bit tougher. All right? So here it is on the screen. This is just another way to find m, those rate orders. Okay, so here's one problem, video problem 9a. You can go through, you can look at this, figure it out. Notice there are 2 reactants and 3 products. Do I care about the products? No. Right? Okay, so determine the reaction's rate law, and then determine the value and the units for the rate constant. All right, that is differential rate laws, or using the initial rates method to find differential rate laws, right? So to find the values for k and to find those values for m and n. It is tough. Okay? The only way to do it is to practice it. And sometimes you'll make mistakes. I made a mistake while I was filming this, right? So you can go through, you can do video problem 9a, you can look at the worksheet number 9. The video solution for 9a will be posted. The answer key for worksheet number 9, here are those extra problems, right? Not more, they'll be posted. And this will be homework number 9. Homework number 9 is on Blackboard. And for that one, again, I'm going to have you write it out and post it. Okay? It's tough. It takes some time, but it's very useful. So go ahead and start working on that. All right, so that is it for lesson 9. Most of you will probably be watching this after the test. So make sure you get in homework number 8, which is due on April 29th, and number 9, which will be due on May 1st. Right? If you're watching this before the test, remember the video to go through the procedures so you know how to do it. All right, talk to you later.